Okay, so the fact of the matter is, however, with like life as we know it depends on having friction present, right? Like we wouldn't be able to walk on the ground if we didn't have friction between our shoes and the ground. We just like, I don't know, we'd be like moonwalking all over the place, right? I don't even know if we'd move anywhere, it'd just be in one spot. Okay, right, so we're going to define static. Here, I'll change the color to red so you guys can know what the answers are. I'm trying to zoom in here too. Static friction, okay, is the force exerted on a stationary object by the surface that prevents the object from starting to move. Okay. It is in these instances that the applied force is equal and opposite in direction to the relative to the static friction, right? So it's like what she was saying in the video, right? The thing with the static force, their static frictional force, it can change its magnitude until you reach that maximum, right? And then it just turns into kinetic, okay? And so depending on how hard you're pushing, right, you're going to be measuring the frictional force differently, okay? The more force you apply, the more frictional force you will see, right? And until it starts to move, okay? The kinetic friction is the force exerted on a moving object by a surface and acts opposite to the direction of motion of the object, okay? And like always, an object can only move / accelerate if F net does not equal 0. Okay, in other words, ma. Okay, so the object's accelerating. Okay. Anybody have any questions so far? It's just me. I just wanted to put some stuff into text for you from the video, right? That video had some nice like illustrations, right, as to like what was going on. Okay, it also talked about 2 factors that affected the force of friction, right? The overall amount of friction that we experience, right? One of which was the type of surface that we were pushing on, right? Or that the object's sitting on, right? So the type of surface, right? Which basically means like how rough is it, right? And then the other thing that affected it was the mass of the object, right? Because we know that the mass of the object, like we saw in the video, and the force of gravity is kind of, it's proportional to mg, right? The mass times the gravity, right? And under certain instances, like let's say on an incline, then it's equal to a component, right, of cosine. Okay, on an incline. Okay, so we can see that the mass is affecting how much friction we're going to experience. And what was this? We know that mu Fn, right? Fn being mg, right? The force of gravity. It's opposite of it. Or the component that we saw. Okay. So we have something that takes into consideration both of these when we calculate the magnitude of the friction, and we're going to call it the coefficient of friction, right? And it can either be static or kinetic. You're going to get 2 different numbers, right? So the coefficient of friction. Okay. Okay, and so we use this Greek letter mu. Okay. How to spell that, I don't know. You guys have to Google that. I can't remember. I don't know. I'm not even going to try and spell it. Mu. You look it up. Okay. And mu is represented by the force of friction divided by the normal force. That's how we would find that. Okay. So as discussed above, we have two types of friction, and thus we should expect to have two types of values, right? We have mu s for static and mu k for kinetic, right? And what it's important to know is that mu values can vary anywhere from 0 to 1, right? And have no units. It's like pi 3.14. It doesn't have any units. It's just it's a coefficient, right? And it doesn't have units because what are we doing here? The units here for force are newtons, and the units here for the normal force are also newtons. And so dimensionally, newtons cancel with newtons. And so we have no dimensions, right? Cancel, right? Which is why you don't see any units down here. Okay. So a value of 0 would indicate a frictionless surface, and a value of 1 would indicate a very rough surface, okay? Or something that's going to experience lots and lots of friction, okay? And so you can see some examples here. Rubber on concrete, well, there you go. You get 0.6 to 0.85, so that's relatively high, okay? And ice on ice is 0.1, that's very, very small. Okay, but they'll never go above 1, and they'll never go below 0. Okay, they're just between 0 and 1. Anybody have any questions before I jump down? Okay, so I just have two examples here, and then once we're done those, you guys are good for today. Okay, and you guys are gonna try some of the questions that are in the Minds Online. Okay, so as always, you can have a read through the question, right? And sometimes I even, like, as I'm reading the question, I'm adding information to my free body diagram. That sometimes helps me as well too, right? It's not so overwhelming. You read the entire question, you're like, okay, what do I do with all this information? Sometimes as I go, okay, 1.4 kilogram block is on a horizontal surface. Okay, so let's take a stop there. Okay, I'm going to draw my block on a horizontal surface, right? And I know its mass is 1.4 kg. Okay. It's being pulled horizontally by an applied force. Okay, well, let's draw an applied force then. We'll call it, that's horizontal. We'll call it FA for applied force, right? And it takes 5.5 newtons to start the block moving and 4.1 newtons to keep it moving, right, at a constant velocity. Okay, let's not necessarily deal with that yet. Let's continue drawing some forces on our free body diagram. Well, I know that I'm going to have a Fg, or a gravitational force, that's equal to mg. And subsequently, if I have a gravitational force, or I'm in contact with a surface, you guys know I have an Fn, equal and opposite in magnitude to this, if it's horizontal or perpendicular, right? And then additionally, we have one other thing, right? We have these forces of friction as well, right? Okay, and our job is to figure out what the coefficients of friction are. Okay, so I want to find mu s and mu k. Okay, that's our job here for part A. Okay, so let's do we'll do mu s first. Okay, the static frictional force. So we know it takes 5.5 newtons to start the block moving. Okay, which means my FA, or applied force, is going to be 5.5 newtons, right? But there's a very split moment in time where we're just trying to figure out the exact moment in time where that object starts to move, right? And up until that point, it's not moving, right? And we know that these two forces here are balanced, right? They're equal and opposite. So if I were to do, oh boy, I'm having a hard time drawing sigma today. Right? It's not moving and it's never going to move in the y direction, right? Those two are always going to be balanced, right? So I'm not too interested with the y direction here, right? What I am interested in is the fact that in the x direction, I'm getting these imbalances in forces. But for the very split moment in time, before the block moves, we're leading right up until the exact moment in time that the box breaks the static equilibrium, right? And so up until that point, we want to know exactly what the frictional force is, the mu S max, if you will. Okay, and so what's that look like? Well, we can sum up the forces in the x direction, and we know it's equal to 0 because it's right up until the moment before it starts moving. Okay, and so it takes 5.5 newtons, right? So while we have a positive applied force, right? And then we know the frictional force is always opposite to the applied force. Well, the applied force is acting in the positive x direction, so then I know that the frictional force is acting in the negative direction, and that's equal to 0. Okay? Then we can say, okay, what is the force of friction? Because we know what FA is. We could plug in right now. We know the force of friction, or the applied force, is going to be 5.5 newtons. Minus, okay, well, we got to figure out what this force of friction is. Well, we know based on the frictional forces, or like the factors that affect the force of friction, that we have the type of surface and the mass, right? Well, with mass kind of comes gravity, right, and weight. So we know that in this force of friction, we're going to have an mg term, right? Because it's weight, right? And that's what it's affecting the amount of friction that we experience. Now, the other factor was, well, how rough is the surface? Well, that's kind of what we're trying to figure out, right? And so we're going to say mu s. And you could label it mu s max if you'd like, right? In this particular instance, that's what we're trying to find. I just don't have enough room. So there you go. There are your two factors. There's weight and how rough the surface is. Well, we're trying to solve for like how rough the surface is, mu, right? And so that's what we're going to do. So you say, okay, I'm just going to move this term to the other side. And I'm going to get 5.5 is equal to mu s mg. Well, mg are two values that you know, so you can plug those in. So 5.5 is equal to mu s, what do we get? 1.4 times 9.8. And so if I were to divide both sides by that, whatever that number might be, then I'd get mu s, or the coefficient of static friction, 5.5 divided by, which should give you 0.4. Anybody have any questions with that? How I got there or anything like that? Okay. Second part here is now I want to find what's the kinetic friction that this thing's experiencing, right? So now we've gotten it moving, and so it requires less force to keep something moving than to overcome the initial static friction, right? And that's what we can see here, right? But the other catch is the object is moving, but they've stated something else in this question. We have an applied force of 4.1 newtons that ultimately keeps it moving at a constant velocity. Well, constant velocity means no acceleration, right? It's just zero slope, right? There's no acceleration. So I also know for this part, if I were to go find for mu k, the sum of the force, sorry guys, I'm getting emails too. It's also equal to 0 under this instance, right? Because if there's no acceleration, it's not equal to ma, right? It's just moving. You're allowed to have things moving. F net equals ma is only if the velocity is changing, if the object's accelerating, right? And so we have this ma. So let's just do the same thing here now, right? We just have basically the exact same question, except that our applied force has changed. And we're solving for a different amount of friction, kinetic, right? Or a different kind of friction. So the applied force is still positive. So you get the applied force minus the force of friction, right? Is equal to 0. Well, it's not 5.5 now. It's 4.1. So 4.1 minus mu mg, we discussed where that came from, the two pieces that affect friction. And that's equal to 0. So then I say 4.1 is equal to mu mg, okay? And then 4.1 divided by mg is equal to mu k. Sorry, guys, I should have been writing the k in. Okay? And so mu k, if I were to plug in the same two values, 1.4 and 9.8, right? Those are the mass and the gravity that the box is experiencing. Then I'm going to get 0.3 for mu k. Okay? Okay, and then let's say we apply it, we're going to attach a rope, which I thought was already attached there, but and we pull was 9.3 newtons. Okay, well, now the box is accelerating, right? So we're not really, it's just going to keep gaining speed and gaining speed, right? So now I know that the sum of the forces, there's an imbalance in the forces, right? So we're going to say, okay, well, I have this new applied force minus the force of friction has to equal ma. Well, what's this new applied force? 9.3 newtons. Minus, the box is, how do you get 0.3? Sorry. So Christopher wants 0.3. Christopher's, I'll just run through this. That's okay. 0.3 should be 4.1 divided by 1.4 times 9.8. Which is mu k. So if you did that calculation, you should get 0.3, if I'm not mistaken. Okay, good. Okay, so now that you guys know what the coefficient of kinetic friction is, this box is moving now for part B, right? So don't necessarily care about the static friction, right? Because the box is moving now. And so it's experiencing 0.3, no units, but a value of kinetic friction there, right? So we're going to say, okay, well, the force of friction is going to be mu, which we just found, right? 0.3. So 0.3 times m, 1.4. Maybe I'll write this out. I'll write this out once. Mu mg 1.4a, right? 1.4 is just the mass. So 9.3 minus 0.3 times 1.4 times 9.8 has to equal 1.4a. And if I were to divide both sides by 1.4, I'm just thinking if I want to bring your attention to something. Let me ask you guys a question, because sometimes I remember doing this in grade 12, and it's a no-no for the current moment. See how I see a 1.4 here and a 1.4 here? Does that mean I could do that? And I want somebody to type in the chat. Can I do this? And call it a day? Okay, mathematically, no, right? And hopefully everybody's on the same page. This will come up, and I remember doing this in grade 12 just because it's kind of one of the benefits of why I'm pretty good at teaching math now, because I know where all these silly little things happen, right? And why you can't do them, right? You can't do that because you have to divide everything by 1.4, which includes this. Okay. If you just cancel them, you haven't divided the 9.3 by the 1.4. So you're going to get a wrong answer. The reason why I bring that up is because what you saw this morning, if I do something like mg sine theta is equal to ma, there's only one term on this side. So if I were to divide both sides by mass, now they cancel, no problems. I don't have anything else over here, right? But in this instance, you'd create a problem for yourself, okay? So everything has to be divided by the 1.4. Okay. Try not to erase anything. Okay. I just wanted to bring your attention to that because I remember doing that. Okay. So if you were to do all that work, you would say A is equal to, so the force of friction, Jagger, here I'll do, let me scoot down here. The force of friction, I'll give you two reasons, right? Let's just think about if something is a force, Jagger, then you better see units of newtons. I'll try this explanation in two different ways, right? Mu, if it's just mu is just a coefficient, right? Like it's just there's no units here. And so dimensionally, we have a problem, right? There's a disconnect between what I'm expecting to see on the left side in terms of units and what I'm seeing on the right side. So that's one reason, right? The other thing is there's two factors there, right? Jagger, there's if you think back to the video, we had this box sitting on the floor. Well, how rough the floor is, that's mu, right? And then we have a whole bunch of different numbers to represent how rough the floor is. That's kind of what we just figured out, right? We found out that this is 0.3 was kind of relatively low. 0.4 is kind of getting into the mid-range, right, for the static friction. But we also learned that, well, it kind of makes sense that if we have this big block sitting on the floor, that it's like the amount of friction it experiences kind of is dependent on how heavy it is, right? Well, we also know that when something's pushed on the floor, there's an equal and opposite force pushing back up, right? What we call Fn, right? And so in reality, I didn't explicitly say, the video said this, but the force of friction is equal to mu Fn. Okay? And the reason why I just write mg is we can solve for what Fn is, and we know that Fn is equal to mg, or the force of gravity, sorry. Because these two things are equal and opposite, right? And what's force of gravity? Mg. So this is my way of kind of shortcutting. Now, I think what we'll see here, if I get to this, no, I won't. This will be another lesson. The reason why I bring this to your attention about it being equal to the normal force is when we get into question, I won't do this right now. When we get into a question that's on an incline, and this is the reason why I introduce inclines without friction first, you're going to have a normal force and the force of gravity acting directly down. But this time, Jagger, if this is Fn, Fn is not equal to Fg. Fn is equal to the vertical component, which will be mg cos theta, because theta's here. Okay, and so when we calculate the friction, I may as well talk about this now. The force of friction for questions like this will still be mu Fn, but Fn is no longer equal to Fg, because Fg is kind of acting straight down, right? It doesn't equal Fg anymore. What is it equal to? Fn is equal and opposite to mg cos theta. And so when we calculate friction for these kinds of questions, which will probably be tomorrow, we're going to see that the force of friction for questions like this is equal to mu mg cos theta. Didn't really want to do that today, but fits into the conversation. Is that helpful? Okay. You always got to think about equal and opposites, right? That's Newton's third law. Okay. So back to this. If I do the math, if you guys have a scientific calculator, what I would do, I would type this verbatim into the calculator. And then whatever that number is, which I didn't write down, but then you just hit answer divided by 1.4, right? And you should see that the acceleration for this is 3.70 meters per second squared. And you don't need the vector because we didn't, well, I guess you could. You could put the vector on if you guys would like in the, I don't know, east direction. Right? We'll say east is positive over here. Anybody have any questions with that? Oh boy, we went over. Okay, let me do this last question. Remember, this is it for today. You guys don't have anything else to do. Kind of got derailed there with some questions. Okay, let me run through this. You guys are good to go for today. Okay? So again, I'm going to draw my floor. Horizontal box. Or not horizontal box, but a box on a horizontal floor. What do I have? I'm going to have the force of gravity. I'm going to have Fn. They should be equal and opposite. Fn. Right? And then I'm going to have the force of friction. And I'll start putting all the numbers and stuff on here after. Okay, and then here's the trick with this question. I'm applying a force of 115 newtons, but it ain't sideways. It's at an angle. I was supposed to do something. Right, so here's my applied force this time. As soon as you see this, you should be thinking components, right? And although components add an extra layer of difficulty, it's the same work all over again, over and over and over again with components. You're finding what's the X piece, what's the Y piece, and separating. That's what projectile motion was really good for. It's a good introduction to stuff like this, right? Where we're like, okay, there's two different motions going on here. Well, there's two different forces acting, right? In different directions, right? So I have 15 degrees here, and I know the magnitude of that force being applied is 115 newtons. Okay, you guys got to find the X piece, and you got to find the Y piece. We know that the block is not going to just jump off the floor, right? It's not jumping off the floor. And so we know that if I were to look at the forces acting in the Y direction, it's not accelerating in the Y direction. So zero, sorry. Okay. And so let's just figure out what's actually going on here. Well, we'll call this force applied Y, force applied X. Well, I'm just going to look at all the forces acting in the Y direction. Well, what's acting in the Y direction? I've got Fn, I've got Fg, and I've got Fay, right? That's all stuff acting in the Y direction. So let's write it down in terms of the directions that it's going, right? So Fn, we have positive Fn because that's acting in the upward direction, right? Keep in mind, you guys can say whatever you want. I just like dealing with the norm, positive, positive, negative, negative. I have a positive FAY, and I have minus FG. And that's going to equal 0. Okay? So, I can figure out what FG is. FG is nice. That's a nice one. FG is equal to M times G. Well, the mass of the box is 45 kilograms. Right? And if you do the math on that, you should get 441 newtons. Well, where's that go? It goes in for FG. Right? And you also know what FAY is. FAY is, here's theta, you look across, oh, there's opposite. You see the word opposite, you know you're using sine. Right? So you're going to get 115 sine 15. Right? Oops, sorry, I got this in the wrong spot. I wrote it differently on my computer. Fn, I don't know. Right? Minus 441 equals 0. So we can solve for what Fn is by moving these two terms to the other side. Or just doing the math and then moving the number, right? But we could do it either way. Fn should be equal to negative 115 sine 15 plus 441. So Fn equals 411.2 newtons. Why did I do that? I did that because I know when I go to solve for the force of friction, we now know that the force of friction is, like you guys know, force of friction is equal to mu Fn. Well, I'm going to need to know what Fn is. But the thing is, if you guys add, like when you apply a force in the vertical direction, even though it's just a small component, the box is now being lifted off the floor a tiny bit. Right? So it's experiencing less friction because of the fact that it's being lifted off the floor a tiny bit. Because of this FAY piece. So that has to be taken into consideration when you find Fn. Right? Fn is the normal force. Like how hard is it pushing onto the floor? Well, that's being affected by the fact that you're pulling up at an angle. So it's not being pushed as hard into the floor, so you better incorporate that into your friction calculation. Right? So now if I look at the sum of the forces in the x direction, right? Right? Okay, well now it's accelerating, right? It's gonna move in the x direction with some acceleration. So that's what I'm trying to find. Okay, and so we're just looking at the forces again. Well, it looks like if I'm looking from left to right, and I think sometimes that's what I typically do, I have minus the force of friction, right? It's acting in the negative direction, plus Fax is equal to Ma. I think I only have the two forces acting in the x direction, right? You guys know what this is. Fax is 115 cosine of 15. Force of friction is mu Fn. So negative mu Fn plus 115 cosine of 15 is equal to Ma. Okay? Question told you, sorry it's getting a bit messy, but it told you what the mu value was, kinetic friction, once it's moving. So it's negative 0.2 times Fn was the 411.2, yeah, plus 115 cosine 15 is equal to 1.4. Was it 1.4? No, that's the other question. 45. 45A. Divide both sides by 45, you have your answer, right? So A will be equal to all of that divided by 4.5. 45. My goodness, I'm rushing to get you guys done. Okay? Once we find the acceleration, question's almost over. Okay? Whatever that number is. Turns out to be, if you guys type that into your calculator, you should get a number of 0.64 meters per second squared. And then this is my favorite part of these kind of questions, is we can take into consideration, I'm just going to move this over. We can take into consideration all the stuff we learned with kinematics. And this question ultimately asked us how much time elapses between the time at which you are pulling it with a velocity of 1.4 meters per second squared. Okay, sorry. Your note will say something different, but basically we want to find, like, saying that the box starts at a v1 of 0 and we pull on this thing and it accelerates for whatever and it finally reaches this 1.4 meters per second. We know Vf is equal to 1.4 meters per second. We know Vi was equal to 0. We now know what the acceleration was, 0.64 meters per second squared. I want to find time. How long did this motion take? Right? So you guys can use the kinematic equation from your sheet. A is equal to Vf minus Vi divided by T. And if I rearrange, I'm going to find that T is equal to Vf minus Vi over A, which is going to, Vi was 0. So I get Vf over A, 1.4 meters per second. Well, I don't need to write that in there. You can if you want, but if not, 2.19 seconds. Are we okay? Sorry that took so long. But that's it. I like these questions because we can combine units, right? From and not units as in like meters per second squared, like kinematics versus forces, right? Together we call that dynamics. Okay. Does anybody have any questions with what's gone on there? So we're combining F equals ma, F equals 0, or F net equals 0. And we're trying to apply this to, I'm going to apply a bunch of forces to this, and the thing's going to move if they're not balanced. How do we calculate exactly how that's moving? That's the acceleration. That's what we're going for. Okay? Does anybody have any questions?